Okay, we're recording here. I close the door. All right, I wanted to show you, people had a question on problem 12 in Chapter 8 as well as problem 15 in Chapter 8. We did talk about this a little bit in class, I believe, already, but let me go through it briefly with you. On problem 12, we have the wire here, which will, I guess I need a pen, don't I? I need a pen, okay, and I need a color. See, I think I've got a color there, don't I? So that wire has a tension T. That's what we're looking for. This mass, the sign down here, we're told is 10 kilograms. Okay. So it has a weight of 10 times 9.8, doesn't it? Okay. Come on. No, cancel that. Uh-oh. Oh, jeez, I gotta start over again here. Okay. So 10 times, oops, back up, times 9.8, okay, or 98 newtons. Okay, so that means there's a force pulling down on this beam, force pulling down right there of 98. I don't know why this keeps doing that. Simply trying to write 98 newtons here. Okay, and the distance from here to that 98, we're told, is half a meter. So we have a lever arm, this lever arm right here of 0.5 times 98. I don't know why it keeps doing that. So it creates a torque this way, right? Due to the sign. The mass of the beam itself is 5 kilograms, so the weight of the beam is 5 times 9.8. Okay. 49. So that's 49 newtons. And that weight is, and at the center of the beam, so that's 1 meter, isn't it? Okay, so 49 newtons times 1 meter, okay, is 49 newton meters. That's additional torque in the clockwise direction. So now that we've got 49 newton meters in from the beam's mass, we've got 98 times a half, or 49 newtons meters in the sign's torque. Okay, so we have a total of 98 newton meters of torque. Okay, now we're told that the angle right here is 30 degrees. So the portion of the tension that is perpendicular to the beam, this portion right here, is T sine 30. T sine 30. Right? And that's acting along the beam's length of 2 meters, isn't it? So the torque due to that force, T sine 30, is the length of the beam, 2 meters, times the force, T sine 30. So we have 2 meters times T sine 30 is the torque in the counterclockwise direction, and that equals the torque in the clockwise direction, which was the sum of this 49 and that and that 98 times a half, which is also 49, so that's 98 newtons. So if you solve that equation for the tension, you'll be able to answer that problem. Let's go down here to the second problem, number 15. We have a frictionless surface, tension of the string pulling on the 4 kilogram mass. So we have the mass here will be accelerating to the right. Have this mass here is accelerating downward, and that mass is experiencing two forces, downward weight and upward tension. And then the pulley itself is rotating, so that pulley is experiencing angular acceleration. Okay. Due to the torque difference between the tension T2 trying to rotate it clockwise and the tension T1 trying to rotate it counterclockwise. There's three objects that are moving, so we have to have three equations. The first equation for the 4 kilogram mass coming from F equals ma would be T1 equals 4 times A. F equals ma applied to the falling mass would be F equals ma. That would be T2 acting upward minus the weight downward, which is 5 times 9.8, which is 49, equals 5 kilograms in the minus A direction. Okay. So there's another equation. So we have one equation up here, we have one equation down here. Okay. We have three unknowns. We have the T1, the T2, and the A is an unknown. The last object that's moving here is the pulley. The pulley obeys the equation torque equals I alpha. Okay, and the torque acting on that pulley is from the center right here. We have a radius that takes you up to the tension T1. T1 is pulling left, so our T1 wants to rotate that pulley counterclockwise, and our T2 wants to rotate that pulley clockwise. That's why it's negative. That's a 1 right there. Okay, and we're going to treat the pulley as a solid disk whose moment of inertia then will be 1/2 mr squared. Whoa. mr squared. I don't know why that keeps doing that. Let's see, do we have an eraser here or something we can... There it is. We're going to erase that tail on that. Okay. Go back to our pen. M r squared. That's I. And then alpha is A over R. So there's another equation. Notice all the R's will cancel out. You have an R over here, an R down here, and two of them there. They'll all cancel out. So if you solve, whoops, what happened there? Okay, well, if you solve the equations T1 4A, T2 minus 49 minus 5A, and T1 minus T2 is 1/2 ma. You can put them all together and solve for the acceleration A. Okay? All right.